So yeah, this is the only slide for today. So basically, I will just quickly show how to set up simsMVA once you download the files and then using MATLAB. And then we have 4 to 5 examples, starting from how to export data from Surface Lab and then process with simsMVA. And I want to kind of increase complexity for each example. So we start with spectra data sets, and then depth profiling, surface mapping, and then 2 examples with 3D mapping. And hopefully using these examples, we'll be able to showcase all the features, the main features of simsMVA. Right, so as I'm not sure whether things are clear, please just stop me whenever it's going too fast or it's not clear, because I will be just showing how I work with simsMVA. Okay, so hopefully you're still seeing this. I'm remote accessing another computer. So the first thing is how to set it up, right? So if you download it, you're going to get all these files. So in MATLAB, just find the folder with all these files. And I think the easiest way then from this point is just go back one folder. So all my files are in this source folder. So what I do is I go back one folder, find it, right click, and then it will be like this, grayed out. So you right click, add to path, selected folders, and then you'll be highlighted in the list. And then that's all right. So once you have done this, you just come to your command window and type in simsMVA. Okay. So now, before we start using simsMVA, let's go back to Surface Lab and see how to export dataset for each of the examples. Right. So the first one, as I say, it's spectra. And I decided to use these carboxylic acids, like we had in one of these slides last week. So basically, these are just repeat spectra of several carboxylic acids, and we want to use MVA to find differences between these spectra. So the first thing to do is, remember, you need to pick variables, right? So basically select the peaks. So I imagine everyone is familiar with this, but the only thing we have to make sure is, because we're exporting data for several measurements, they have to be consistently calibrated. So the way I do this is I set up an overlay. So I only include these ones, the ones I'm interested in the overlay, by, I'm not sure if you know, by pressing V here, so it will kind of fill in with the color. And then I come and make an overlay here in the high resolution view. All right, so once these things are consistently calibrated, what you can do is make a pick list based on all the spectra. So obviously today is not about making pick lists, so just apply the list I made previously called all acids. So add your active spectrum, and then you have here, I imagine everyone's familiar with this again. So what I do is I just check for all the peaks roughly if they are spanning the right peaks, you know, because here this is applied for only for adipic P2, but when I see them in the overlay, I can see whether or not it's getting areas for all the spectra, meaning that they are consistently calibrated. So once you make sure this is the case, the next step is the quickest way to get these areas for all the ones is you come to the left-hand side list here, select everything, like I hold Shift, click first, first is this one, click the last, and then highlight all the selected ones, and then come back to your pick list here. There's a button on the left-hand side called Pick Statistics on Selected Spectra. So I click that, and then it comes up with this table, right, which is the matrix we spoke last week. So if you're doing this for the first time, you may have a different setup. So what you have to do is select the second one here, pick data in rows, because it may come like this with the peaks in columns. So you change it to rows. Then all these buttons here to do with which value you're going to get for the area. So this is the original, the time corrected area. But for this case, in most cases, we can do already normalized by total area intensity, which is this one here. So you click it, if you see, they turn into very small numbers. And also at the end of the list, you get the total counts. If you keep it there, you have to remove it afterwards. So what you can do is just untick this box here, and then you remove the total counts at the end. So that's what you get. So what you can do now is just save it as a text file. So second button here. Yeah, I have saved it before. So we'll call this 2. So acids, positive, normalized 2. And that's it. So if you do it, making sure you have this sort of setup, it should be okay to load in simsMVA. Right, so now we go to simsMVA, come to new tab, because these are spectra, we select spectra, and then we can name it, so acids, and then you see that it creates a tab here at the top named acids. So to load the data, you click this first one here, which is new list. So yeah, so you go load file, find it. So I saved it here. That one, right? Acids, positive, normalized 2. And then open. Just say discrete because we have a pick list. Okay, so what you get is this table inside the same table. So, and the first thing I always do is for spectra is because I have repeats of measurements, I want to group them, you know, when I plot stuff. So I click this third button here, which is set groups. And then if you have repeats of the same measurement, you want them to be plotted with the same colors, you just name them the same. So you can go like carboxylic, tricarboxylic, and I think I have, yeah, so let's just copy. Right, so these are like the categories, right? And they all repeats of the same measurement. So here we're already making an assumption that things will not change. Any change will be statistical variation. And then you'll see when you do OK that the column names will change. So before we do any MVA, it's quite useful to use this sometimes. So here you have all your list of peaks. So if you select, like, let's say 1, 2, 4 of them, and click this correlation matrix, it will create these scatter plots. Remember when we spoke last time, like that's PCA is based on the correlation between all these peaks. So this is called the correlation matrix, where you get a scatter plot between every pair in a matrix, and then you measure sort of this slope of a linear fitting of all the points. So these numbers here are sort of the correlation you get between the pairs of variables. So like between C5H9 and C12H11 or 1, I think it's 11. It's 0.28. So sometimes it's good to explore. Even after you do MVA, you come back to this to make sure things are making sense. You know, maybe there's an artifact here because you see it's not exactly linear. That's another problem with sims. So you may give you some weird results. So, and also if you select too many obviously it will be difficult to plot. So like it's 10. Let's do several of them. So remember those numbers, the correlation index. If you do it now, when there's too many, it will not show the plots, but it will just show this correlation matrix as an image. So coded to from negative to positive correlation. So you see wherever you have green, very green boxes, means that those peaks are extremely correlated. So PCA will take this into account, and so it's quite likely these will, for example, will be together in one of the loadings, for example. And also things that go purple mean are peaks that are anti-correlated, so more with one, less of the other. Right. So remember, before we do, let's do PCA for this date. So before we do anything, we have to pre-process, right? So it's already normalized by total because that's how we export it. So we don't have to worry about this, but we have to Poisson scale and mean center. So in this box here, you have a few options for your pre-processing. So we'll select Poisson scaling plus mean centering. So you see here on the top, the original data, and at the bottom, the pre-processed. So it's Poisson scaled and mean centered. So that's the new average of your data. So obviously it's centered around 0. And that's it. Now you're ready to do PCA. So that's the PCA button. You can see the symbol is just showing that rotation we discussed last week. You click there. If you don't select anything, these are algorithms and retaining components, etc. If you just go run, if you do the standard method, and then it creates a new tab with the results. Okay, I will stop for 5 seconds if there's any question, because I'm not sure if it's going too fast. Okay. So in this tab, you always, whenever you do MVA in simsMVA, you get always 3 panels. So the top one here is showing the loadings, and the one on the bottom left is the scores, and then the variance. So if we first look at the variance panel, it's showing the variance captured per principal components. So as I said last week, it's ordered in terms of the variance. So obviously the first PC will always show the highest explained variance, as we say, and then it decreases for the high to the high ones until it's really close to 0. So there are a few rules to set to define which are the relevant PCs. One of them is whenever you go over 95% of total explained variance, the other principal components will be noise. So I always add this value here as well to guide us where this happens. But not necessarily this is always the case. Sometimes you have relevant things over 95 or not relevant things under 95. So that's how you use this panel here to explore the variance per principal component. And also, if you use this to present this data to anyone, it's good to use this to justify why you pick this specific principal component and why you believe it's not noise, because it shows a lot of variance. So in the loadings, you have a few drop-down menus. So this one here is to select which principal component. So PC1, 2, 3, 4, right? And then you see all the labels. If you want to see the masses instead of the labels, you click this one. It will change. It's inverted, but yeah, when you click, it will show the masses. So this slider here is for setting up a threshold for which labels you will show. So if you go very low, it will show everything. If you go very high, it will just show maybe the highest one or none of them. So you can use this to explore which peaks you want to see the labels. It's also quite useful to use the split. Yeah, so the split separates positive from negative. So obviously it's still first principal component is just another way to visualize it. You know, if you don't want to see things pointing downwards, you just split, and then you see the negative contributions and the positive contributions. There are a few other buttons, but let's now move on to the scores panel, right? So here you have two scatter plots for the principal components. So here it's a 2D, the other one is a 3D. So if here in the y-axis you pick one of the principal components, you see it a function of sample number. So you're just seeing the values for PC1, and that's when your interpretation starts, right? You see that it's quite high in the positive for malonic acid. So PC1 positive is quite likely representative of malonic acid, right? I mean, the ions you see here in the loadings. So if you come back to the loading and see these peaks here, okay, these are the characteristic peaks of malonic acid. And then you can do this for all the principal components, like this succinic, glutaric. I think number 4 is, yeah, number 4 you have a contrast between pimelic in the negative and adipic on the positive, right? So if you go PC4, it peaks pointing into the negative side. They're more characteristic of pimelic, and positive to adipic. And as I said last week, it's very useful to do scatter plots between principal components. So let's pick 2, 3, and 4, for example, or 1, 2, and 3, right? But the succinic is not showing well when to do 1 against 2. But if you look, so let's do 4 instead of. So if you look in the 3D here, you see that they're clearly separating in groups. And obviously these are very different. They have very different patterns in the secondary ions. So it's a good one to validate the methodology. So that's why you get this. So yeah, here you also have the malonic. All the other ones are in the center because most of the principal components are almost like exclusive of each one of them. So you won't see those groups really well. But if you do like 3 against 4, yeah, depending on which one you pick, you will see those groups in this kind of 2D plots, and in the 3D you see that they're clearly separated. I mentioned last week the biplot. Just one way to put the loadings together with this course. So there's a button here for that. So if you click this, it will show the biplot both for the 2D and the 3D scatter plot. And then there's a slider here to set which ions you show, because when you have a long pick list, the biplots can be very messy. Right, so like the low intensity ones will be there and you don't see anything. So if you do something like 50% or anything like this, you only see the most characteristic. So now in a single plot, you can see how they group and also which are the characteristic ions of each group. Right, so here they're grouped by which acids they are, right? So it's just confirming that these are different acids that we measured and knew they are different acids. But that's how it works. And you can also, you remember these scatter plots with the original variables, you can also do it with the principal components. If you click this plot matrix, so let's say 4 components, it will create that same sort of scatter plot for each of the principal components. So like every pair. And in the diagonal, you have these distributions. So it's just all these scatter plots together. And you can also have this sort of general view with the loadings if you use the grid button here at the top. So if you say I want to see 4 in a 2 by 2 arrangement, it will bring you these plots, and if you zoom in one of them, it will do it for the others. Yeah, finally, you can, when you set up groups like this, sometimes you have several repeats for each group. So if you use this average button, it will reduce them to single points, 1 point representing the average point of each group. So to make it easy to see, there's another thing I should mention, like these buttons here in the top right of each panel, you create a new window with the results. Sometimes it's easier to see things, right? You can just expand it as much as you like. So if I average, you see that now they are just single points. Remove the average, they go back to their groups. Yeah, just groups, average, single points. And these are the confidence intervals based on the group distribution. You can remove it as well or include it. Okay, so that's the end of the spectra example. So I will leave a few seconds for questions again. Don't know if it was too fast.
Gustavo, we have a question.
Okay.
It's asked by Adi. We understand that we don't Poisson scale Orbi data, but do you still mean center the Orbi data before we do PCA?
Yes. PCA requires the mean centering. Otherwise, if you remember, it will the first principal component will show you the mean percent, the average of your data, right? So if you don't mean center, you're always going to get the average for principal component 1. So regardless of the nature of the data, it can be Orbi or TOF. Okay.
Right. Thank you, Gustavo.
Yeah, so let's do it. Like, there's just Poisson scale. It looks like this. So if you do PCA now, creates another one. So it creates an additional tab, and this first principal component is just the average, right? And then you look at these scores, kind of looks like it's increasing with the size of the assay, or it doesn't mean anything, you know, it's just showing the average. Then you go to the next ones, they may show the real chemistry, but you already changed everything by not mean centering, so you may be missing important information. So to delete a tab, you just right click and then go delete. Okay, so now let's move on to the depth profile. So one level of complexity further down, it's now you have data that's structured, right? Each point is related, spatially related, because they're coming from different depths. So for that one, I will use this depth profile for a printed device with several layers. So again, you must be familiar. In this case, you only have one file. So what you can do is search all the peaks within the total spectrum of your file. And if you don't know how to do this, it's quite easy. You just click this peak search button, and then you can set the mass interval, some rules for the minimum counts, minimum signal to noise, etc. Then you go search, and then it will bring you all the peaks. And then you can just add all the peaks to your list. Mine's already here, so I'm not going to do it again. But once you do this, with Surface Lab 7, which I believe is the one everyone's using, you don't have to reconstruct your data. So once you do this, it's already present there in the depth profiling. So going from the Spectra, I use the Spectra window to create the pick list, then go to the depth profiling software to look at the profiles. So here, what you get is all the profiles from your pick list. And I imagine you know how to explore your data using Surface Lab. So to export, you go, once you, I think the quickest way is once you can do it, like here I'm doing like 10 points averaging, no, I'm summing, yeah, compressing every 10 points, normalizing, etc., etc. I'm not showing the total. So once you have something that you're happy with, you can go File, Export, and just give it a name. So, and then you can just say use display configuration, because then it will keep all these operations you performed for your data. You click OK, and it creates a text file as well. And then you're ready to go back to simsMVA. So now you click New tab, Profiles, and let's call this Device. You go there, it's empty. You use that same button to load your profile. Go load the file, then find it. So we just exported this one, right? So let's see, you select it. So each, depending on the version, it exports data differently of Surface Lab. So I had to add this option. So just if you're using Surface Lab 7, like we're using now, you say Surface Lab 7. And then it will create, it will load everything. So here you can see your data, same way you see in Surface Lab. So not too useful, you can use Surface Lab for that. But what you can do is explore ways of normalize. So you can normalize by the total over the maximum of each profile. But because we already normalized this data in Surface Lab, it came with the counts already corrected or normalized the way you wanted. So you can also apply the moving average for, like, we did apply some averaging before, where you can do extra averaging using this slider here. Be careful, because if you average too much, you lose all the structure. So it becomes meaningless. It's just, yeah, not going to. So I will remove all the averaging, moving to the left. So let's for the depth profile, let's do NMF, right? So remember, NMF is non-negative, so we shouldn't mean center, but because this is tof data, we have to Poisson scale. So,
Gustavo?
Yeah?
We have a quick question regarding point-to-point normalization. What is what do we use as a reference for point-to-point normalization? Is it the total count?
Yeah, I mean, depends on what you want to show, right? But for the purpose, oh, actually, this was not as a reference. Maybe someone picked this up. Yeah. So what you in this case, I thought I was using the total, but yes, you can use any ion, right? But if you planning on doing MVA to correct for topography, like we discussed last week, you use the total. Yes.
Thank you again.
Right. So yeah, Poisson scaling, and then you click these other button here, which is the NMF, so it's showing the matrix factorization. So now differently to PCA, you cannot just click run. You have to set up some things. So you don't have to worry about the first two drop-down menus at first, but you have to say how many end members are there. Remember, you need to input this. So as we discussed, we could do PCA first and then estimate it based on the PCA results, or based on what you already know about your sample. So in this case, actually, we printed 4 layers of material. So it's a good first guess to say, okay, let's try with 4 end members. And because it's an approximation, you need to set the number of iterations. So, you know, sometimes it takes longer to achieve convergence. So with depth profiling, it's all right because the data is not too big. So you can do something like 500. And here, if you select calculate lack of fit, it will show you the improvement after every iteration. It takes a bit longer, but when you're not sure about things, it's good to have this so that you know how many runs you need for, you know, to factorize your data. So once you're happy with the parameters, you just click run, and then you run it for your data. And then when it's done, it will create a new tab. Yeah, there was something weird with that. Maybe because I didn't normalize by total before. So I have a backup. So I loaded before with more peaks. It's just because it's too heavy to load with more peaks and it takes longer to export. So I didn't want to waste all time just exporting it, waiting for it to export. But once you have a longer list and import it with the proper normalization, that's what you get. It's just a much longer list. So let's do exactly the same. Put some scaling, normalize by the total, and then NMF. So it's the same data set, it's just more peaks. So 500, lack of fit. Yeah, so it takes a little bit longer because it's just more peaks to process, but it's still all right. Okay, so it's same structure as before for PCA of spectra. Now it's NMF of profiles, but the top panel here is showing now the end members contribution. So obviously there's no negative contribution, but apart from this, it works in the same way. You have the threshold here for showing the labels, and you can select which one you want to see of the ions, etc. So it's exactly the same. Here at the bottom, it's a bit more simple. What you get is this table here to select which ones you want to show, and then you can further normalize it. You know, because these are non-negative, so you can normalize by the total again to make everything add up to 100% at each level. Or you can normalize by the maximum of each profile, so everything maxes at 1, or you can just keep it like this. So in terms of interpretation, it depends. You know, we have to look at the ions and think about the chemistry of each one. So you see that the purple here is number 4. It's intense at the interface, so these peaks are likely present at the interface. And 1 is just, it looks like it's once you've gone through the sample, so it's probably the substrate. So you go to 1, you see like it's got like sodium, some other stuff. It's probably the glass light substrate. There's not much in terms of visualization of depth profiling results. You can change things to log scale in Y, in X as well. Sometimes you want to see detail of the first few levels. Or you can also do this overview, which is a way of showing everything. So you click there. When you get this window, you can add things to this overview. Those being the NMF end members, and then you get this window with kind of an overview of your results. One thing that's useful for depth profiling is that sometimes you don't want to process even though you exported the entire profile, you don't want to process the first few levels. So there's this set range button. So you click it, it pops up a window where you can just click the beginning and end of the area of the regions you want to process. Then it will become blue like this. So now when you do NMF, you will disregard this first 8,000 or more seconds of sputter time. So let's still say all this. There should be 4. Oh yeah, I forgot to say, instead of variance, when you do NMF, you get here the lack of fit, so like the quality of your fit after each iteration. So you can see that after more or less 100, it's not improving much. So it's probably converged to some local minimum. So obviously, if you did like 1, 2, 3, 4, 5 iterations, it's not enough. There's lots of room for improvement. So that's how you see whether or not you need to run for longer. Like 500 was the result I get at 500 is probably very similar to the result I would get at 200 because it's not changing much. It's converging. So now you see here it's just showing the data at the interface, and then you can see it shows sort of 2 layers at the interface. And if so, I said we printed 3 materials, right? So we had the substrate, the first one, second one, and the thick one on the top. So now instead of processing all the other layers that are supposedly the same, we're just processing the points at the interface. So it helps sometimes. But apart from this, everything else is the same. The end members, etc., and how to deal with the data. Okay, so yeah, that's it about the depth profiling, how to explore and process. You can do this PCA as well. You know, it will give you exactly the same sort of results, but things go into negative. But just to save time, we'll move on to the imaging example. So yeah, so before I move on, we'll give again 5 seconds for questions. Yeah. Right, so now imaging. I selected this adhesive data set. So similarly to the depth profiling, as you know, when you have an imaging data set, you can create a pick list. So again, you can use the pick search using the total spectrum to find the strong peaks. Create a list and then move onto the imaging software. So there you're going to have your full list of maps on your right hand side, and you can use Surface Lab to process. But what we want today is to export it so that we can use it in simsMVA. So similarly to the depth profiling, you go File, Export, and now you get this list here on your left hand side. And it depends on which ones you want to export, but if you want to export all of them, just Control A, select everything, and then leave these unchanged, all scans, unless you want to export specific scans of a profile or anything like this. And then all these scans will be added together into a single image. There are 2 formats you can export it to load into simsMVA. So one of them is something called BIF6. It's a binary format. The other one is again text file showing like the XY coordinates and intensity for the ions. So if you select the binary BIF6, let's pick a folder. Yeah, sorry, you click the target folder, you can click the select and just pick a folder. So this imaging adhesive. So you can change the name of your file, or just keep it the same so that you know which one, where it came from, and click export. So it will not tell you when it's done. So what I do is like whenever I can move this window again, it means it's been exported. So for some large data sets, it takes a while to export. So try to move this window. So I think the quickest way to test whether or not it's been exported. So if you go to the folder, you see it created a single file, which is like 12 megabytes, containing all the maps from your ion. So one map for each ion. So the other option, as I said, is to do the ASCII text file. So you can create a folder for that. So when you go target folder again, you just name it, select that folder. And the reason I'm creating a folder is that when you use the text file option, you will create one text file for each of the ions. So here we have we have 198. So we're going to have 198 files plus the total. So it's good to have it in a folder, so it's easy to, it's just for me, it's easy to keep it organized. So when you click export, so let's try to catch this. So you go into the folder. Yeah, it's already done. So it just generated all these files, right? They contain the same information as this binary file we created using the bif6, but now it's just one for each. So we can load both structures into simsMVA. So this is already exported. So we go now back to simsMVA, not this one, the one. So we go new tab, images now, adhesive. Looks the buttons are the same, so you know which one you use to load this one. And we're going to load a file, so load file. So now you get these options, right? You can use a bif6 or an ASCII file, and the stitching option, which we will not discuss today. So let's do first the bif6. So we go bif6. It does the pre-compression factor. If it's not too big data set, you can set to 1. It's all right. So you find the folder again. So that's the file, right? Sample 7 codes here. Before it loads, when you click OK, it will ask whether you want to crop it. It depends. If you have corners with, edge effects or charging or things like this, it may be good to crop so that you don't take those errors into account. If not, you just say no. If you load the entire image, then you get a warning for the amount of memory it requires. And yeah, so we loaded the bif6. Before we do any processing, let's load the ASCII as well, so you can see. We created a new tab. Load. Now ASCII files. We have to skip the total. I'll probably fix this, and it's just because it's getting the mass from this label, so it will crash now if we do total. It's a bug. I'll fix that. So I'm skipping total, and then you see it loads ion by ion. So that's you get one image for each ion. So like see the 22.99 both, right? So so it doesn't matter which one we use. So let's stay here. So let's see. Let's first talk about the normalization, right? So now because we cannot export it already normalized, so you have to normalize yourself. So you can see your total intensity here in this one where we managed to load it. that's the total. So what we can do is normalize it by total. So it should be constant. Yeah, everything is 1. So it's a confirmation that the normalization is working. So go back to the 29, you see it's a bit more flattened, right? So if there's any topography in there, it's been corrected by this normalization. So I will remove the normalization. So we'll go back to the first one here. Yeah, this is before, and this is after the normalization. Yeah, in this case, not that much different, but it's good to do it. So the other ones are related to, first one, to compressing. So similar to what you get in Surface Lab, you can reduce the number of pixels by joining pixels together. So the good side is you increase the signal to noise ratio because the counts per pixel, because every 4 pixels now are becoming 1. But obviously, if you go too much, you start to lose the spatial information. The other one is not joining pixels, so it keeps the same number of pixels, but it moves the data. So small degree sometimes is good to kind of cancel out some noise. But again, if you go too high, you start to blur until you get to the point where you just don't have your real data anymore. And then again, the same pre-processing options. So let's do PCA first. So we have to Poisson scale and main center, right? So here you see your data changed. At the bottom here, you see data inside this red square. If you want to explore stuff, yeah, again, you will calculate inside the square.
Gustavo, quick question.
Yeah.
So regarding binning and smoothing just now, with binning, you mentioned that it improves the signal to noise ratio.
Yeah.
Do we also get an improvement in signal to noise ratio with smoothing, or is it just for binning? Thank you.
You do, but it's more related to what to the spatial resolution, because the idea of smoothing is averaging as well. Instead of binning, you're joining pixels together. It's moving. It's almost like averaging pixels together, but without getting rid of the neighbors. So like for each pixel you get, it's like 4 neighbors around it, and then average the number. So that's why it blurs, because you're just mixing the signal. So the expectation is that when you do this, because noise is random, you cancel the noise. So in a way, you're improving the signal to noise ratio, but not necessarily improving the counts per pixel, and most certainly decreasing your spatial resolution because you're moving it. So yes, there are good sides, but you have to be careful.
Understood. Thank you.
All right. So yeah, so we're ready to do PCA, right? We selected the appropriate pre-processing. So we go and click the PCA button. So for PCA, again, we don't have to worry about changing things for now. Just go run, creates a new tab. And as always, now you get variance here, loadings, and scores. When I do PCA of imaging dataset, the first thing I do is actually use this first drop-down menu in the loadings, which I didn't mention before, because it's now relevant for imaging. I select a color scheme. So let's say diverging 2. So it's green, purple. And then I do the same for the scores, because as I said last week, it helps in the visualization and identification of the patterns when you have the same colors. So this top one here it's the color scheme. So you say diverging 2. So you see things will go from green to purple, right? With centered more or less around 0. So now it's quite easy to identify that purple stuff related to those peaks and green to those other peaks. And again, here you have a drop-down menu for going through your principal components. So this is 1, 2, 3. There's maybe contamination. And I must say, like, if you don't like the green, purple, a few of the options like this red, blue, and this pink, green, etc., etc. So here you see the scatter plot is same as we get for the spectra, but remember now each sample, each pixel is a sample. So you have as many points as pixels you have here, so around 16,000 points. So and here I'm plotting PC1 against PC2. So if I change here, I'm changing the X. So now PC3 against PC2. So if I put PC2 in the first one, PC3 in the first one, and PC1, or PC2 in the second one, that's what you get, right? So, and the X is PC3, so all the pixels with positive in the PC3, they should be purple. So these are likely those pixels, and you can confirm this by using the brush function. So you click brush, and come to your scatter plots and just highlight the pixels you want to see in the image. Yes, see, you created this orange area here. We can also do it like, let's say, where are the negative in PC2? I'm not seeing the PC2 image, but I can still identify where they are using the brush. Oh yeah, inside those features. And the positive PC2, for example, kind of this edge here. So sometimes the brush is useful to identify these common regions. If you click brush again, it resets it, or if you do anything, it just resets it. Now, I don't know if I mentioned it last week, but yeah, I think I did. It's negative values sometimes are confusing. So what you can do, like as I mentioned, you can split the loadings just to visualize the positive contributions and negative. You can do the same with the scores, right? You can separate anything from 0 to negative into another map. Always remember, it's still the same principal component, you know, you're just separating the way you visualize things. So there's a button here for splitting. And you see that this diverging column map doesn't look good at all for the splits, because now you don't have negative values. So you have to get a more linear column map, such as the blues, which will be orange because it's inverted. Yeah, it's the blues, it's orange named blues. So yeah, so now you can see only the negative contributions and relate it to these peaks here, the green ones, and the positive and relate it to the, so now instead of color matching, you're doing like left, left, right, right matching, right? So these features are related to those peaks. So like you can do the same for PC2. Yeah, the edge and the inside. The PC1 was like kind of everywhere against these features. PC2 is edge of the features against inside of the features. And PC3, if you remember, is the contamination. So contamination against everything else. All right. So it depends. Really depends not only on your preference, but also of the data set you're using. Some of them are like I like to use the diverging non-split for this one because it shows quite well the regions, but that's not always the case. Also, you see here you have loads of principal components. So if we go, let's say, to number 55, look, it's noise, right? So that's what you get. Your data is full of noise, but when you do PCA, the images will look really nice without noise because you keeping all the noise in the other principal components. So the contrast you achieve by doing PCA is always much better than just imaging two specific ions, because you're adding all the ions together with a specific ratio, and the noise is all down in the other principal components. Well, it's already 1 o'clock. I have the other examples. I think I should ask if everyone still got time, or we should do it another time. I'm fine doing this. I just don't want to, overdo it.
Goose. I think David has just left the chat, but we have a question from another user, Viren. Are we able to produce a 3D PC plot for the image analysis? Any chance?
Yeah, I mean, we are using simsMVA. No, like there's no button to do that, but yes, you could do that. So we could do a 3D plot with 3 principal components. It may be a good thing to add as well if people find it useful. And yes, maximum is 3D, but yeah, it can be useful. Not right now. We have to kind of go back to MATLAB and do it, but at the moment with simsMVA you cannot do it, but it's possible, definitely. Yeah, similar to the Spectre case. Okay, so I don't know. So should I continue then, Akmal?
It depends. David didn't say anything unless people wish to do it, like we can do a third session because then more users can continue, or do we still want to continue right now? It really depends on what other people think about it.
Yeah, I'm not seeing if people are leaving or, just I will trust you as my chair.
A few people have left.
Too many people.
I think Misha recommend a sensible suggestion. Maybe we can do a third session so that more people can join in case that we can continue this and record it. But I think if people have questions, it would be quite difficult for them to join the chat. Maybe we can ask David if we can do a third session for next week. Is that okay with you?
Yeah. So what's missing is I will do NMF with the imaging and then show the 3D. So it may take even less time next time, the half an hour, I don't know. Depends on questions and things like this.
Okay.
Okay, so should I stop then?